Okay, so we're looking at indirect proof and inequalities on one triangle. Okay, so an indirect proof is like a four-step process. You are not going to have to write indirect proofs as part of this course, but we're going to prove a couple things using them. So one, you have to identify what is to be proven. Two, you assume the opposite. Three, you show the assumption. Leads to a contradiction. And finally, you conclude the opposite is false, which proves your initial statement is true. All right, so let's give an example of this in a kind of straightforward way here. Okay, so we want to prove that a right triangle does not have an obtuse angle. Okay, so here's my right triangle. So it's an arbitrary right triangle. We're going to call it, we'll call that L, we'll call that J, we'll call that K. So we're going to be given that triangle JKL is a right triangle. We want to prove that triangle JKL does not have an obtuse angle. Okay, so one, we know what we want to prove. We want to prove that JKL has no obtuse angle. So we assume the opposite. Assume that triangle JKL has an obtuse angle. Okay, well, there we go. All right. And we're going to assume that that angle, without loss of generality, is going to be angle K. All right, so we're going to build a little proof here. Statements, reasons. Okay. Well, we know from this drawing that the measure of angle K plus the measure of angle L has to equal 90. Okay, because acute angles of a right triangle sum to 90. All right, that's fair. That means that the measure of angle K is equal to 90 minus 90 minus the measure of angle L. It's subtraction. But we also would say that the measure of angle K has to be greater than 90, because that's the definition of an obtuse angle. And that's our assumption, is that K is an obtuse angle. Okay, so this means that 90 minus L has to be greater than 90. That's just substitution. this means that, well, if we work this around, the measure negative the measure of angle L has to be greater than 0, which means that the measure of angle L, so that's subtraction again. The measure of angle L has to be less than 0. That's by division. And there lies our contradiction. The measure of an angle cannot be less than 0 degrees. So this is our contradiction. If that contradiction is there, then step 4 is saying, hey, we have a contradiction, so our assumption is false. So that means that ultimately JKL does not have an obtuse angle, because if it did, then we would have to have an angle that measures less than 0, which we can't do. So no obtuse angles will be allowed. All right, so we get a couple of inequality theorems here at this point, and we're going to use some of this logic to prove some of them. Okay, so the first theorem that we're going to get here involves a triangle that has 3 different side lengths. Okay, and we'll call this thing Q, R, and S. And basically the theorem says is that the larger angle is opposite the largest side. So the largest side in this thing is QS. That means the largest angle has to be R. The medium side is RS, which means that the medium angle has to be Q. And the smallest side is QR, which means that the smallest angle has to be S. So we're going to be given that RS is bigger than RQ, so we're being given the sides. We want to prove then that the measure of angle RQS is bigger than the measure of angle S. Okay, so RS is bigger than RQ. That means that RQS has to be bigger than the measure of angle S. All right. So what we're going to do to prove this is we're actually going to locate P on the segment RS so that RP and RQ are the same length. So P is going to be around, it feels a little too high, maybe around here somewhere. There's P. So we have RQ and RP being the same length. Okay, so if I stretch this, there's an angle 1, there's an angle 2. If those are the same length, then this is an isosceles triangle, which means the measure of angle 1 has to equal the measure of angle 2. All right, so we also know that the measure of RQS, let's call this one the measure of angle 3, we know that the measure of RQS has to equal the measure of angle 1 plus the measure of angle 3. That's by the angle addition postulate. Okay, so from here we know that the measure of RQS has to be bigger than the measure of angle 1. Because if I'm adding angle 3 to 1, this has to be bigger than 1 all by itself. So if RQ is S is the sum of these, it has to be bigger than the measure of angle 1 just by itself. Okay, so since 1 and 2 are the same size, I can say that the measure of angle RQS has to be bigger than the measure of angle 2. That's just substitution. Okay. Now, if you can recall, we said that if I have a triangle with a tail, right? So we want to look at this really carefully here. if I have a triangle with a tail. So here's my triangle, and there's the tail. The sum of the interior angles, so the measure of angle 3 and angle S has to be equal to the exterior angle. So the measure of angle 2 has to equal the measure of angle 3 plus the measure of angle S, and that's by the exterior angles theorem. So what do we got here? If this is bigger than angle 2, then the measure of angle if 2 is bigger than 3 plus S, then the measure of angle 2 has to be bigger than the measure of angle S. And if RQS is bigger than 2 and 2 is bigger than S, then the measure of angle RQS has to be bigger than the measure of angle S. That's basically a transitive property. So that's what we were setting out to prove. We've kind of worked step by step through it, and we've got it. So the big side has to be across from the big angle. The smaller side has to be across from the smaller angle. So let's suggest that we want to write the converse to this. Okay, so we're going to start with another triangle here. Maybe we'll call this one let's call this P, Q, and R. And now we're going to start with the angles. So this is going to be the converse. Given that the measure of angle P is bigger than the measure of angle R, we want to prove, okay, so what's across from P? P is across from QR. So we want to prove that QR has to be bigger than whatever's across from R, which is QP. And so I'm going to prove that QR is bigger than QP. Okay, so what we're going to do is we're going to use this indirect proof idea. So we're going to assume that QR is not bigger than QP. Okay, so this implies either that QR is smaller than QP or QR is equal to QP. Okay, so let's look at case 1. Case 1 is that QR is smaller than QP. Okay, this means that from the last theorem, if QR is smaller than QP from the last theorem, then the measure of angle P would have to be smaller than the measure of angle R, but that's a contradiction. That contradicts our given. Our given says the opposite, so that cannot be true. Case 2 is that QR is equal to QP, but if that's the case, then the measure of angle P has to be equal to the measure of angle R, because this would be an isosceles triangle. QR equal to QP means I would have an isosceles triangle. These two angles would have to be the base angles. They're equal. That again contradicts my given. So if the two cases both contradict the given, then my assumption here has to be false, which in fact implies that QR must be greater than QP, which is what I'm trying to prove. So by using the indirect proof method here, I can get to the end of the game much faster. Alright, so we're going to leave that behind for a minute, and we're going to get to something called the triangle inequality. Okay, so the triangle inequality tells me that if I have some triangle, let's call it A, B, C, then so I'm going to be given a triangle A, B, C, then the following have to be true. That AB plus BC has to be greater than AC. AB plus AC has to be greater than BC. And AC plus BC has to be greater than AB. Now note, one side of this triangle is larger than the other two. Okay, so in this case it's AB. So we can automatically get that AB plus another side is going to be bigger than the third. So that's not really the question here. The question is if I take AC plus CB, so it's this one, AC plus BC has to be bigger than AB. That's the one that's really in question here. Is that necessarily the case? Okay, so let's look at how we're going to prove this. I'm going to find a point out here called D. And the formal proof of this is in your notes, but I'm just going to kind of walk it through. It's on the same line as AC, and it's going to make this BD and BC congruent. So I'm going to pick that point. Label this angle 1 and angle 2. And because that there is an isosceles triangle, that means that one, let's see, what do we do here? I take this back. I'm building that point not so that these two are congruent, but rather that BC and DC are congruent. Those two. There we go. So we're going to call that 1. We're going to call that 2. That's an isosceles triangle. That makes these two congruent. So I have that angle 1 has to be congruent to angle 2 by our construction here. Now note, because D is on this line, AC plus DC has to equal AD. That's by the segment addition postulate. All right, so let's take a look at some other things that are going on here. We're going to label this one angle 3. Okay, and we have that the measure of angle ABD has to equal the measure of angle 2 plus the measure of angle 3, because that's the angle addition postulate. Those two have to make up that one. So we can get an inequality here. We can say that the measure of angle ABD has to be bigger than the measure of angle 2, because if I'm adding something to angle 2, then in getting this, then ABD has to be bigger than 2 by itself. But up here we said that 2 and 1 are the same size, so we can substitute. The measure of angle ABD has to be bigger than the measure of angle 1. Okay, that's cool. So this means that AD, so this guy down here, AD, has to be bigger than AB. Why is that? Because 2, right? Sorry, ABD is here, right? That's got to be bigger than angle 1 is here. So this is telling me that the segment AD has to be bigger than the segment AB. And that's from the converse theorem that we just proved moments ago. Okay, so if I've got that, but I know that AD is AC plus DC, and that has to be bigger than AB, but by construction, DC has to be the same length as BC, so AC plus BC have to be bigger than AB, and voila, there we go, we have proven the triangle inequality. So any two sides of a triangle have to be bigger than the third side. So you can't just pick up 3 sticks and make a triangle. 2 of them always have to be bigger than the third one, no matter what, no matter what, no matter what. All right, so there you go. indirect proofs and inequalities in single triangles.